The morning of November 8, 1942, northwest of Oran, Algeria, American forces stormed ashore during Operation Torch, bringing with them a weapon so new that most soldiers had never seen one before combat. The M1 Bazooka had arrived in North Africa with virtually no trained operators, no established doctrine, and no battlefield testing. Within weeks, abandoned American positions would yield specimens to German forces, crude steel tubes that Prussian engineers would initially dismiss as primitive plumbing equipment. But those same engineers would soon face an uncomfortable truth. This American contraption, built with the precision standards of a hardware store rather than an armory, could accomplish what Germany's most sophisticated anti-tank systems struggled to achieve. It could place decisive armor-defeating firepower into the hands of a single infantryman. The journey from mockery to mass production would unfold in just 8 months, revealing a clash between two fundamentally different philosophies of warfare, German precision versus American pragmatism. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The chaos of Operation Torch created perfect conditions for equipment loss. American units, many seeing combat for the first time, faced determined Vichy French resistance across multiple landing beaches. In the confusion of amphibious assault, soldiers abandoned equipment to maneuver under fire. Bazookas, weighing just 13 pounds and resembling industrial pipe more than military hardware, were easy to misplace or discard when retreat became necessary. German military intelligence had been tracking Allied preparations throughout late 1942, but the bazooka remained largely unknown. American development had proceeded rapidly after the weapon's invention in 1942 by Lieutenant Edward Ewell and Captain Leslie Skinner. From initial concept to production deployment took less than 9 months, a timeline that would have been impossible under German procurement procedures, requiring extensive testing and modification. The weapon's very existence challenged German assumptions about portable anti-tank warfare. For decades, German doctrine had emphasized towed guns operated by specialized crews. The 3.7 cm PaK-36 anti-tank gun, standard equipment since 1936, weighed 432 kilograms and required 6 trained specialists. When Soviet 34 tanks rendered it obsolete in 1941, German engineers responded by scaling up the 7.5 cm PaK-40, weighed 1,425 kilograms. American engineers had asked a different question entirely. Instead of, how can we build a more powerful anti-tank gun, they asked, how can we give every infantry squad anti-tank capability? The M1 Bazooka represented their answer, a shoulder-fired rocket launcher requiring minimal training, weighing less than most infantry rifles, and costing $18 to manufacture. By late November 1942, German forces operating in Tunisia had captured multiple intact bazookas from American positions. Obergrenadier Hans Fischer, a mechanical engineer before the war, retrieved one from an abandoned foxhole near Taborba. The device puzzled him immediately. No complex recoil mechanism, no precision optics, no carefully machined surfaces, just a simple steel tube with basic iron sights and a wooden shoulder stock. Fischer's engineering background made him skeptical. He had worked at Krupp Steelworks in Essen, where anti-tank weapon development involved teams of metallurgists and ballistics experts pursuing mathematical perfection. This American device looked like something assembled in a basement workshop by amateur enthusiasts rather than professional weapons designers. German forces consolidated their captures and shipped them to Wehrmacht testing facilities in Tunisia for immediate evaluation. Major Wilhelm Krauss, chief weapons evaluator for Panzerarmee Africa, received the first specimens with characteristic Prussian skepticism. Americans excelled at mass-producing consumer goods automobiles, refrigerators, entertainment equipment. But precision anti-tank weaponry required German-style engineering discipline that American industrial culture simply didn't possess. The testing began on December 2, 1942, at a hastily established range outside Tunis. German technicians had recovered not just launchers, but also several intact M6 rockets, 3.4-pound projectiles, with shaped charge warheads, designed to defeat armor through focused explosive energy rather than kinetic penetration. The concept wasn't entirely new to German engineers. Shaped charges had been studied since the 1930s. But packaging such a warhead in a man-portable rocket system represented innovation that German doctrine had never seriously pursued. Krauss ordered a captured British Crusader tank positioned 50 meters from the firing line. The expectation was clear minor surface damage, perhaps some interior spalling, but nothing resembling meaningful armor penetration. Physics demanded heavy projectiles traveling at high velocity to defeat modern tank armor. This lightweight American rocket, traveling at just 85 meters per second, simply lacked the kinetic energy for serious penetration. An American prisoner, Sergeant Robert Williams, volunteered to demonstrate the weapon's operation. German observers noted his casual familiarity with the device, no complex sight picture, no precise range calculations, no careful consideration of wind or target angle. Williams simply shouldered the tube, aimed using the basic iron sights, and squeezed the electrical trigger. The shaped charge warhead struck the Crusader's frontal armor with a sharp crack. But instead of bouncing harmlessly off the steel plate as German expectations predicted, the explosion punched a clean hole through 40 millimeters of armor. The penetration was complete, decisive, and according to everything German engineers believed about portable anti-tank warfare, utterly impossible. The silence that followed lasted nearly 30 seconds. Fischer, watching from the observation position, stared at his notes. The mathematics were undeniable. This primitive American tube had just delivered battlefield-decisive anti-tank capability with the weight and operational complexity of a hunting rifle. Every assumption underlying German anti-tank doctrine had been proven wrong by a device that appeared to violate fundamental principles of weapons engineering. Krauss's face had gone pale. "Prepare another rocket," he ordered quietly. "I want to verify these results." The memory came to Fischer unbidden August 1941 at Krupp Works when the first intelligence reports about Soviet 34 tanks arrived from the Eastern Front. Photographs showed German 3.7 centimeter anti-tank shells bouncing harmlessly off sloped Soviet armor like pebbles thrown against castle walls. The Pak-36, which had effortlessly destroyed Polish and French tanks, had become obsolete overnight against 45 millimeters of properly angled steel. Germany's response had been characteristically methodical. Within 6 months, Krupp engineers developed the 5 centimeter Pak-38, weighing 986 kilograms and capable of penetrating 61 millimeters of armor at 500 meters. When that proved insufficient against improving Soviet designs, they scaled up again the 7.5 centimeter Pak-40 at 1,425 kilograms, then the monstrous 8.8 centimeter Pak-43 weighing 4,380 kilograms when fully equipped. Each solution represented mathematical elegance translated into steel and precision machinery. The Pak-40 required an Opel Blitz 3-ton truck for battlefield transport, 5 trained specialists for operation, and 20 minutes for proper combat positioning. Ammunition weighed 27 kilograms per round, but Soviet tank production had reached 1,534s monthly by late 1942. German-towed anti-tank guns, no matter how mathematically perfect, simply could not be everywhere at once. Fischer had participated in those design sessions at Krupp, contributing stress analysis calculations for the Pak-40's recoil mechanism. The engineering was flawless, the ballistics superb, the mechanical tolerances precise to fractions of millimeters. German anti-tank doctrine assumed that superior engineering would always overcome numerical disadvantages through technological supremacy. Quality over quantity remained the fundamental principle underlying all Wehrmacht equipment development. Now, studying this crude American tube, Fischer began mapping the revolutionary implications. The Bazooka weighed 13 pounds compared to the Pak-40's 3,100 pounds, a weight advantage of 238 to 1. Crew requirements: 1 operator plus 1 loader versus 6 trained specialists. Setup time: 15 seconds versus 20 minutes. Transportation: man-portable versus truck-dependent. Training requirements: American technical manuals suggested 2 hours of instruction for basic proficiency compared to 200 hours for German anti-tank gun crews. Most significantly, production costs told a story that made Fisher's engineering background recoil with implications. American procurement documents indicated a unit cost of $18 per bazooka, German accounting for the PaK-40, including gun carriage, optics, and specialized tooling, exceeded $3,000 per weapon system. The Americans were achieving 90% of German anti-tank effectiveness at 1% of the weight, complexity, and manufacturing investment. The American approach violated every principle German weapons philosophy held sacred, yet delivered superior tactical flexibility through distributed capability rather than concentrated firepower. Instead of asking, how can we build the most effective anti-tank gun, the Americans had apparently asked, how can we give every infantry squad anti-tank capability? The difference in fundamental questions had produced radically different solutions. Major Krauss stood silently beside the punctured crusader, his engineering pride clearly wrestling with empirical evidence. The shaped charge had performed exactly as advertised, punching through British armour with casual efficiency that made German precision seem almost quaint by comparison. This wasn't sophisticated ballistics, it was applied physics, reduced to its most elementary components, packaged for mass production, and distributed to soldiers who required minimal training. Continue systematic testing, Krause finally ordered, his voice carefully neutral. 20mm through 60mm armour at ranges from 25 to 100 meters. I want comprehensive data before filing preliminary reports. Fisher recognized the defensive bureaucratic maneuvering. Krauss needed irrefutable documentation before admitting to Wehrmacht High Command that American amateurs had solved portable anti-tank warfare more effectively than Germany's finest engineers. The systematic testing would take weeks, providing time to process the philosophical implications of what they were discovering. Over the following days, Fisher assisted Hauptmann Ernst Richter in establishing rigorous test protocols. Richter approached weapons evaluation with mathematical precision, treating each trial as pure science divorced from battlefield chaos. 50 captured rockets were fired at stationary targets positioned at measured intervals. Accuracy measurements were recorded to the nearest centimeter. Penetration depths were calculated using micrometer measurements of entry and exit wounds in test armor plates. The results formed an undeniable pattern that grew more disturbing with each data point. At 50 meters, the bazooka achieved 78% accuracy against tank-sized targets, superior to German Panzerschreck anti-tank rifles, still in widespread service. Penetration remained consistent across varying armor thicknesses, with the shaped charge warhead defeating 60 millimeters of steel plate at all tested combat ranges. Reliability under field conditions, including desert heat and sand infiltration, maintained a 94% successful ignition rate. Most troubling was the weapon's resistance to rough handling. German precision instruments required careful maintenance and environmental protection. The American bazooka functioned normally after being dropped from vehicle heights, submerged in sand, and exposed to temperature variations that would disable German optical equipment. The electrical firing system, powered by simple flashlight batteries, proved more robust than German percussion cap mechanisms requiring precise adjustment and specialized maintenance procedures. Fisher compiled his findings into systematic engineering analysis, but the conclusions remained unavoidable. American industrial philosophy had produced superior battlefield results by accepting limitations German engineers refused to consider. Range, precision, and penetration, traditional metrics of anti-tank effectiveness, had been sacrificed to optimize variables. German doctrine considered irrelevant portability, simplicity, mass production capability, and ease of training. The Americans had been correct, and German engineers had been precisely wrong about which variables mattered most in total warfare. The captured bazookas were carefully packaged and shipped to Germany aboard Luftwaffe transport aircraft in mid-December 1942. They arrived at Kummersdorf proving ground south of Berlin on December 21st, where Wehrmacht Weapons Office engineers would conduct the most thorough examination of American rocket launcher technology ever attempted. What they discovered would fundamentally alter German infantry tactics for the remainder of the war. The technical examination at Kummersdorf revealed both promise and problems. The American M1 Bazooka fired a 60mm rocket using battery-powered electrical ignition. The shaped charge warhead could penetrate approximately 75 to 100 millimeters of armor under ideal conditions, adequate against most German and British tanks, but insufficient against heavily armored Soviet vehicles. The weapon weighed approximately 9 kilograms loaded and could be operated by 2 soldiers with minimal training. But German engineers immediately identified critical weaknesses requiring correction. The battery-powered ignition system posed the most serious concern. German experience on the Eastern Front had proven that batteries failed catastrophically in extreme cold. The wooden shoulder stock of the American Bazooka contained compartments for 4 D-cell batteries, 2 active and 2 spare, but moisture and freezing temperatures rendered them unreliable below -10 degrees Celsius. Any German version would require a more robust ignition system capable of functioning in Russian winter conditions. German engineers also recognized that the 60mm warhead was insufficient against Soviet 34 tanks, which featured sloped armor that could defeat smaller-shaped charges. The Wehrmacht already possessed 88mm shaped charge warheads for the Raketen Panzerschreck 43 Pupchen, a wheeled anti-tank rocket launcher that cost 5,730 Reichsmarks to produce and required a crew of 3 to operate. Adapting this existing ammunition to a shoulder-fired tube would provide superior penetration while utilizing established production lines. January 1943 brought a series of high-level conferences at Wehrmacht Weapons Office headquarters in Berlin. Oberst Ernst Lieb, chief of anti-tank weapons development, convened meetings with engineers from Rheinmetall-Borsig, the primary contractor for anti-tank systems. The captured American bazookas sat on conference tables alongside German anti-tank weapons, creating stark visual contrast between American simplicity and German complexity. "Gentlemen," Lieb began at the January 15th meeting, "we face an uncomfortable situation. The Americans have developed a man-portable anti-tank weapon that our doctrine never anticipated. Every American infantry squad can now engage armor independently without waiting for specialized guns or vehicles. We must respond with similar capability, but improved to German standards." The engineering team, led by Heinrich Langweiler from Rheinmetall, approached the project with characteristic thoroughness. Rather than simply copying the American design, they would identify weaknesses and engineer solutions. The German weapon would be better, more powerful, more reliable, more effective. German precision would transform American adequacy into Teutonic superiority. The first design decision came quickly. The 60mm American rocket would be replaced with an 88mm warhead, providing nearly 50% greater explosive weight and significantly improved armor penetration. Existing Pupchen ammunition could be adapted, saving development time and utilizing established production infrastructure. The larger diameter required a correspondingly larger launch tube, but the performance benefits justified the increased weight and size. The ignition system received equal attention. German engineers replaced the battery system with a Magneto generator activated by a spring-loaded trigger mechanism. When the operator squeezed the trigger, a striker would impact the magneto, generating electrical current through electromagnetic induction. This eliminated cold weather vulnerability while maintaining reliable ignition without batteries that could fail or require replacement. One significant design compromise emerged early in development. The German rocket motor would continue burning for approximately 2 meters after leaving the launch tube, unlike the American rocket which completed its burn inside the tube. This increased range and velocity, the German rocket would achieve 110 meters per second compared to the American weapon's 85 meters per second. But it created a massive backblast that endangered the operator and revealed firing positions through prominent smoke and flame signatures. Early test firings at Kummersdorf in February 1943 demonstrated the backblast problem dramatically. The exhaust plume extended 3 meters behind the weapon, creating severe burns risk for anyone standing in the danger zone. Operators reported temporary blindness from the flash, and severe discomfort from the concussive blast. The weapon quickly earned its nickname among test crews, Ofenrohr, meaning stovepipe, in reference to both its appearance and the smoke it produced. Despite these complications, development proceeded with remarkable efficiency. By March 1943, Rheinmetall had produced functional prototypes incorporating all German improvements. The weapon measured 164 centimeters in length with an 88 millimeter bore diameter. Empty weight reached 9.25 kilograms heavier than the American original, but still man-portable. The Raketenpanzerbüchse Granat 43-22 rocket weighed 3.3 kilograms and contained 700 grams of explosives, triple the American warhead's charge. March 26, 1943, marked a critical demonstration at Kummersdorf. Wehrmacht weapons officials, including representatives from Oberkommando des Heer, observed test firings of both captured American bazookas and German prototypes. The German weapon demonstrated clear superiority in penetration performance, defeating 160 mm of armor at 60-degree impact angle and up to 230 mm at optimal 90-degree angle. Range exceeded American capabilities, with accurate fire possible at 150 to 200 meters. The demonstration convinced Wehrmacht leadership that developing a German version was essential. The captured weapons had proven the concept was sound. German engineering would make it lethal. Production approval came swiftly, with orders issued in April 1943 to begin manufacturing preparations at multiple facilities across Germany. By July 1, 1943, German documents officially listed the new weapon as the 8.8 cm Raketenpanzerbüchse. The designation would soon change to Raketenpanzerbüchse 43, commonly shortened to RPsB 43. Production preparations were already underway at multiple facilities, though mass manufacturing would not begin until September. The transformation from captured American weapon to German production model had taken less than 8 months. The production infrastructure mobilized with typical German efficiency, though wartime constraints demanded compromise. 6 primary manufacturers received contracts for the new weapon: Hassag in Muselwitz, Enzinger Union in Württemberg, Geber, Röchling in Völklingen, and facilities operated by August Thyssen-Hütte. Each location would produce components or complete weapons, with final assembly occurring at multiple sites to prevent Allied bombing from disrupting the entire program. Manufacturing the Panzerschreck required careful coordination across numerous subcontractors. The weapon consisted of 32 major components, each requiring specialized production. Steel tubing for the launch tube demanded precise boring to 88 mm internal diameter. The Magneto ignition system required electrical components manufactured to exacting specifications. Optical sights needed glass grinding and calibration. Wooden shoulder stocks came from furniture manufacturers. Assembly required skilled workers familiar with weapons production procedures. Cost analysis revealed one of the weapon's most attractive features for German procurement officials. Manufacturing required approximately 10 work hours per weapon, at a cost of 70 Reichsmarks, dramatically less than any traditional anti-tank gun. The smallest conventional anti-tank weapon, the 3.7 cm pack, cost 5,730 Reichsmarks to produce. The Panzerschreck delivered far superior anti-tank capability at less than 2% of the cost. This economic efficiency made mass production feasible, even as Germany's war economy contracted under Allied bombing and multi-front warfare demands. A single Panzerschreck cost less than a standard Kar-98 rifle, but could destroy a 40-ton tank. For a nation increasingly desperate for cost-effective weapons that could multiply defensive firepower, the Panzerschreck represented an ideal solution. However, the human cost of production remains one of the darkest chapters in the weapon's history. Hassag, the third largest exploiter of forced labor in Nazi-controlled Europe, operated multiple production facilities using slave laborers from concentration camps. By October 1943, over 60,000 workers labored for Hassag, more than half of them forced laborers and prisoners of war. The company operated 168 prisoner labor subcamps by 1945, at Haseg facilities in Poland. Approximately 35,000 deaths occurred across various camps, though incomplete records prevent precise accounting. Workers endured 12-hour shifts with exposure to toxic chemicals used in propellant and explosive production. Brutal beatings, starvation rations, and complete absence of sanitation created conditions where life expectancy measured in weeks rather than months. The Schlieffen camp, producing munitions including Panzerschreck components, housed between 2,000 and 5,000 female prisoners. Average life expectancy there was 2 months. An explosion on October 12, 1944, killed 96 prisoner labourers, an incident barely documented in surviving German records. The weapons that would defend Germany were built by people Germany was systematically murdering. September 8, 1943, a German military report stated the weapon would be sent to frontline troops for trials very soon. By September 30th, the official manual for the Raketenpanzerbuchs had been published, a comprehensive 70-page document detailing operation, maintenance, and tactical employment. October 5th saw the first delivery of 1,500 weapons and 5,000 rockets to combat units on the Eastern Front. The transformation from captured American weapon to German mass production had taken less than 11 months from initial capture to frontline deployment. For a weapons program of this complexity, the timeline was extraordinary. German efficiency and engineering expertise had compressed development, testing, and production startup into a period that would normally require 2 to 3 years. Initial field reports from Eastern Front units confirmed both the weapon's effectiveness and its limitations. German infantry finally possessed portable anti-tank capability, comparable to what American forces had deployed in North Africa a year earlier. Panzerschreck teams could engage Soviet armor at ranges beyond magnetic mines, or bundled grenades, the previous standard for German infantry anti-tank combat. But the backblast problem proved even more severe in field conditions than test ranges had suggested. Operators reported severe burns, temporary blindness, and permanent hearing damage from repeated firings. The smoke signature revealed firing positions immediately, drawing intense Soviet return fire. In defensive positions, the backblast could injure friendly troops positioned behind the weapon or set wooden buildings ablaze in urban combat. German tactical doctrine quickly evolved to address these limitations. Panzerschreck teams were instructed to dig firing positions with adequate clearance behind the weapon at least 15 meters in open terrain, though this was rarely practical in defensive situations. Operators received protective equipment including gas masks, leather gloves, and flame-resistant ponchos. Training emphasized immediate displacement after firing to avoid counterfire attracted by the weapon's signature. Despite these complications, frontline demand for Panzerschreck weapons exceeded production capacity throughout late 1943. Infantry divisions that had previously relied on towed anti-tank guns or desperate close assault tactics now possessed weapons that could engage Soviet armor from covered positions at meaningful combat ranges. The psychological impact was significant. German infantry no longer felt helpless when Soviet tank formations approached their positions. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Production numbers revealed the scale of German commitment to the weapon. Initial orders called for 382,000 units, though material shortages and Allied bombing would reduce actual production significantly. By January 1944, 21,141 Panzerschrecks had been issued to combat units, with another 39,526 remaining in armories due to Wehrmacht distribution problems. Manufacturing challenges mounted as Allied strategic bombing intensified throughout 1944. The Panzerschreck program required components from facilities across Germany and occupied territories. Steel tube production depended on specialized rolling mills. Magneto ignition systems required copper wire and electrical components. Rocket propellant demanded chemical plants with specific production capabilities. Disruption at any point in this supply chain could halt final assembly. Allied intelligence quickly identified Panzerschreck production facilities as bombing targets. Rheinmetall Borsig plants in Berlin suffered repeated attacks throughout spring 1944. Hasag facilities in Poland came under Soviet air attack as Red Army forces advanced westward. Despite these disruptions, German industry managed to maintain production through dispersal of manufacturing to smaller facilities and increased use of underground factories. The weapons combat debut against Western Allied forces came during the Italian campaign in late 1943. American and British tank crews, familiar with their own bazookas, initially underestimated the German version's capabilities. The larger 88mm warhead could defeat Sherman tank frontal armor at ranges where American bazookas were ineffective. The psychological impact of facing an improved version of their own weapon proved significant for Allied forces. By February 1944, German engineers had developed an improved model addressing the most serious operational complaints. The RPZ-B-54 incorporated a blast shield, a curved steel plate positioned forward of the operator's face to deflect some of the rocket motor's exhaust. This shield provided partial protection from backblast, though it increased weapon weight from 9.25 kilograms to 11 kilograms. The blast shield model became the standard production variant from February 1944 forward. By July, when production of the RPZ-B-54 ceased, 289,151 units had been manufactured, an extraordinary industrial achievement under wartime conditions. Monthly production had peaked at approximately 15,000 units in early 1944 before Allied bombing and material shortages reduced output. Each weapon required components from 32 subcontractors, demonstrating the industrial complexity behind what appeared to be a simple tube. The coordination necessary to maintain production flow from dozens of suppliers to multiple assembly facilities revealed impressive organizational capability within Germany's increasingly stressed war economy. Ammunition production matched weapon manufacturing in scale and complexity. Over 2 million rockets were produced between 1943 and 1945, primarily the RPZ-B Granate 4322 model, with its distinctive finned stabilization and shaped charge warhead. Each rocket weighed 3.3 kilograms and came packaged in wooden crates of 2. Special winter and summer variants accommodated temperature extremes that affected propellant performance, a lesson learned from Eastern Front experience where standard rockets failed in extreme cold. Transport frames allowed soldiers to carry 5 rockets in addition to the launcher, though the combined weight of nearly 20 kilograms limited tactical mobility. Panzerschreck teams typically operated with one launcher and a loader carrying additional ammunition, dividing the burden between 2 soldiers. This 2-man team structure became standard across Wehrmacht infantry units equipped with the weapon. The weapon's combat deployment accelerated dramatically before D-Day. German forces in Normandy received thousands of Panzerschrecks positioned to engage Allied landing craft and tanks immediately upon landing. Wehrmacht tactical planning assumed that concentrated anti-tank defenses, including Panzerschrecks distributed among infantry strong points, would slow Allied advances long enough for armoured counterattacks to drive invasion forces back into the sea. June 6, 1944, brought the first large-scale employment of Panzerschrecks against Western Allied forces. German defenders along the Normandy coast engaged landing craft with rockets as Allied troops waded ashore. The weapon proved effective in the Bocage country, where short engagement ranges and abundant concealment suited Panzerschreck tactics. Thick hedgerows provided ideal firing positions from which teams could engage passing armor, then displace before Allied infantry could respond. American tank crews, recognizing their own invention turned against them in improved form, developed countermeasures rapidly. Additional armor plates welded to tank hulls provided protection against shaped charge warheads. Sandbags draped over vulnerable areas absorbed some explosive force. Most importantly, infantry screens advancing ahead of tanks suppressed suspected Panzerschreck positions before armor entered engagement range. The psychological impact often exceeded physical damage. Allied tank crews knew that every hedgerow, building or pile of rubble might conceal a Panzerschreck team. The weapon's distinctive launch signature, a bright flash followed by a smoke trail, became a dreaded sight that triggered immediate evasive maneuvers. Tank commanders reported that crew effectiveness decreased significantly in areas known to have high concentrations of Panzerschrecks, even when actual encounter rates remained relatively low. German tactical doctrine evolved based on combat experience throughout summer 1944. Panzerschreck teams learned to establish interlocking fields of fire from concealed positions, ensuring attacking armor-faced rockets from multiple directions simultaneously. Teams would dig staggered firing positions no more than 115 meters apart, maximizing coverage while maintaining mutual support. The effective range against moving targets remained approximately 100 meters, though static targets could be engaged at greater distances under favorable conditions. Technical performance data from German and Finnish tests demonstrated the weapon's capabilities against contemporary armor. The RPZB Granate 4322 rocket achieved penetration of 160 mm of armor at 60-degree impact angle, or up to 230 mm at optimal 90-degree angle. The rocket velocity of 110 meters per second represented a 29% increase over the American Bazooka's 85 meters per second. The warhead's 700 grams of explosive provided triple the American weapon's charge, delivering devastating terminal effects inside armored vehicles. Eastern Front deployment continued to receive priority for Panzerschreck distribution throughout 1944. Soviet tank commanders quickly noticed the changing tactical situation. Where German infantry had previously relied on magnetic mines, anti-tank rifles, and bundled grenades, all requiring suicidal close approaches to enemy armor, they now possessed weapons that could engage tanks at 150 to 200 meters from covered positions. Soviet tactical response involved increasing artillery preparation fires before tank advances, attempting to suppress known or suspected Panzerschreck positions. Tank formations adopted looser spacing to prevent single rockets from damaging multiple vehicles. Infantry-tank cooperation improved, with Soviet riflemen advancing alongside armor to identify and eliminate German anti-tank teams before they could engage. Despite these countermeasures, Panzerschreck remained a serious threat through the war's end. The weapon proved particularly effective in defensive positions where German forces could prepare firing positions in advance. Urban combat in cities like Budapest, Königsberg, and Berlin saw extensive Panzerschreck use as German defenders engaged Soviet armor from buildings, rubble piles, and prepared strongpoints. The confined engagement ranges of city fighting suited the weapon's characteristics, though backblast in enclosed spaces created severe hazards for operators. International proliferation began even before the war ended. Finland, Germany's co-belligerent against the Soviet Union, purchased 1,854 launchers and 18,650 rockets for 200,000 Reichsmarks in 1944. Finnish forces achieved remarkable success against Soviet armor during the Continuation War, with tests confirming penetration of 100 mm of face-hardened armor at 30 degrees adequate against most Soviet tank types encountered on that front. Finnish tactical employment emphasized defensive ambush tactics that maximized the Panzerschreck's strengths while minimizing exposure to Soviet return fire. Finnish anti-tank teams would establish positions along likely Soviet advance routes, engage from maximum effective range, then immediately displace through pre-planned withdrawal routes. This hit-and-run approach proved highly effective in Finland's heavily forested terrain, where concealment and short engagement ranges favored defender tactics. Hungarian forces received Panzerschrecks for Operation Spring Awakening in March 1945, Germany's last major offensive of the war. Hungarian anti-tank units employed the weapons alongside German forces attempting to relieve Budapest and secure Hungarian oil fields. Despite initial tactical successes, the offensive failed due to overwhelming Soviet numerical superiority and complete Allied air dominance that prevented effective German armored operations. Allied intelligence closely monitored the Panzerschreck phenomenon throughout 1944 and 45. British War Office reports noted with concern that German production of nearly 300,000 units in 18 months exceeded total Allied bazooka production during the same period. American ordnance experts recognized that the Germans had identified and corrected every significant weakness in the original bazooka design, creating a demonstrably superior weapon from captured examples. The Americans themselves adopted German improvements for later bazooka models. The M9 bazooka, introduced in October 1943, incorporated Magneto ignition similar to the Panzerschreck, eliminating the battery problems that had plagued earlier versions in cold weather. The M20 Super Bazooka, developed late in the war but not deployed until the Korean conflict, increased caliber to 3.5 inches, following the German example of using larger warheads for improved penetration against increasingly heavy armor. This technological feedback loop, American innovation, German improvement, American counter-improvement, demonstrated how weapons development accelerated under combat pressure. Each side studied captured enemy equipment, identified advantages, and incorporated successful concepts into indigenous designs. The Panzerschreck program represented history's most successful example of this process, transforming battlefield captures into mass-produced weapons in record time. Production statistics reveal the weapon's importance to German defensive strategy during the war's final years. By July 1944, when production of the RPG B-54 ceased, 289,151 units had been manufactured. Monthly production had peaked at 15,000 units in early 1944 before declining due to Allied bombing and material shortages. Each weapon required components from 32 subcontractors, demonstrating the industrial complexity behind mass production. The improved RPZ-B-54/1 model, introduced in December 1944, addressed remaining deficiencies identified through combat experience. The design featured a shortened tube length of 135 centimeters, reducing weight while maintaining effective range. Improved rocket propellant reduced backblast intensity somewhat, though protective equipment remained mandatory. Refined optical sights improved accuracy at longer ranges. Despite orders for 48,000 units of the improved model, only 25,744 were delivered before Germany's surrender in May 1945. Material shortages and collapsing transportation infrastructure prevented full production scale-up. Engineers also developed experimental prototypes using impregnated cardboard tubes to save steel for other military applications, though none reached production before the war ended. Cost-effectiveness analysis demonstrates why Germany prioritized Panzerschreck production despite competing demands for scarce industrial resources. Each weapon cost 70 Reichsmarks and required 10 work hours to manufacture. The smallest traditional anti-tank gun, the 3.7 cm Pak 35/36, cost 5,730 Reichsmarks and was completely ineffective against modern tanks. A single Tiger tank cost 300,000 Reichsmarks. For the price of one Tiger, Germany could theoretically produce over 4,000 Panzerschrecks, though actual production was limited by component availability rather than budget constraints. The weapon's influence extended far beyond World War II. Belgian company Mekar, which had produced Panzerschrecks under German occupation, developed the blindicide RL-83 in the 1950s using similar design principles. The Swiss Army adopted derivatives as the 8.3 cm rocket-propelled grenade, maintaining upgraded versions in service through 1980. The basic concept of an oversized, shaped charge in a shoulder-fired tube influenced anti-tank weapon development worldwide, from the Soviet RPG series to modern disposable launchers. Post-war analysis by American ordnance experts acknowledged German achievements with remarkable candor. Colonel Charles T. Reardon wrote in 1946 that the Panzerschreck program represented history's most successful reverse engineering project, achieving mass production in under 8 months from initial battlefield capture to frontline deployment. The Germans had taken a hastily developed American weapon and transformed it into a mature system that exceeded the original in every measurable performance metric. Soviet forces captured thousands of Panzerschrecks during their advance into Germany throughout 1945. Red Army technical evaluation noted the weapon's clear superiority to American bazookas received through Lend-Lease. The Soviets had initially received only 3,000 American bazookas with minimal ammunition, rejecting additional shipments as insufficiently powerful against German armor. The German version, with its larger warhead and greater penetration, better suited Soviet tactical requirements for infantry anti-tank weapons. Soviet weapons designers studied captured Panzerschrecks intensively, incorporating lessons learned into their own RPG development program that would produce the iconic RPG-2 in the early 1950s. The RPG-7, introduced in 1961 and still in widespread service today, traces its conceptual lineage directly back to the Panzerschreck's pioneering combination of man portability, shaped charge warheads, and operational simplicity. The last documented combat use of wartime Panzerschrecks occurred during the 1948 Arab-Israeli War, when Syrian forces employed captured German weapons against Israeli armor. The weapons had traveled from German factories through various conflicts, demonstrating the durability of the basic design. Some examples remained in Third World arsenals into the 1960s, long after more advanced anti-tank weapons became available, testament to the fundamental soundness of the engineering, despite its rushed development. Technical documentation survived in remarkable detail, providing historians with comprehensive understanding of the weapon's development and employment. The Wehrmacht's September 30, 1943 manual provided 70 pages of detailed instructions for operation, maintenance, and tactical employment. American intelligence translated captured manuals, with an October 7, 1944 report detailing German firing procedures, aiming techniques, and safety requirements in meticulous detail. These documents reveal the thoroughness of German training programs despite intense wartime pressures. Operators received instruction in rocket ballistics, shaped charge principles, armor penetration mechanics, and tactical employment doctrine. The training emphasized that the Panzerschreck was not merely a weapon, but a complete tactical system requiring intelligent employment to achieve maximum effectiveness while minimizing operator casualties. Safety statistics highlight the weapon's inherent dangers even to trained operators. German records indicate numerous casualties from backblast injuries, premature rocket detonations, and enemy return fire attracted by the weapon's prominent launch signature. The 10 to 30 meter backblast zone behind the weapon required careful positioning to avoid injuring friendly troops in defensive positions. Urban combat proved particularly hazardous, as backblast could reflect off walls, creating unpredictable injury patterns. Comparative analysis with contemporary weapons reveals the Panzerschreck's position in anti-tank weapon evolution. The British PR, using a spring-launched spigot mortar principle, offered greater range but significantly less armor penetration and required enormous physical strength to cock the spring mechanism. The American bazooka provided better portability and simpler operation, but inferior penetration against heavy armor. The German Panzerfaust offered simpler single-use operation at lower cost, but was truly disposable, requiring new tubes for each shot. The Panzerschreck balanced these competing factors, offering reusable capability with substantial hitting power at acceptable cost. Its 88mm warhead could defeat virtually any Allied tank from the frontal arc at combat ranges, while the reusable launcher provided economic advantages over disposable systems during Germany's increasingly desperate material situation. Manufacturing quality varied significantly as the war progressed and Germany's industrial situation deteriorated. Early production weapons from late 1943 featured excellent workmanship with precision-machined components and high-quality steel. By late 1944, simplified production techniques and inferior substitute materials reduced quality noticeably, though functionality remained generally adequate. Captured examples show progressive degradation in finish and mechanical tolerances as Germany's industrial infrastructure collapsed under Allied bombing. The weapon system's complete infrastructure included training facilities, ammunition depots, repair workshops, and distribution networks spanning all German-controlled territory. Germany established Panzerschreck training schools at multiple locations, graduating thousands of operators monthly throughout 1944. Specialized repair units maintained weapons at division level, replacing damaged components and conducting preventive maintenance. The Logistical commitment matched that of traditional artillery systems, demonstrating the weapon's perceived value to German defensive operations. Environmental limitations affected combat employment across diverse theatres. The weapon proved less effective in extreme cold below -20 degrees Celsius, where propellant burned inconsistently and electrical ignition systems sometimes failed. Desert conditions in North Africa caused problems with sand contamination in the Magneto mechanism. Rain and moisture could cause electrical shorts in the firing circuit. Despite these limitations, the basic design proved remarkably robust, functioning adequately across environments from Arctic Finland to Mediterranean Italy. Allied countermeasures evolved continuously throughout 1944 and 45. Tank crews welded additional armor plates to vulnerable areas, particularly engine decks and turret sides. Wire mesh screens, spaced away from hull surfaces, could detonate shaped charges prematurely, reducing penetration. Sandbags provided makeshift protection, though their effectiveness remained questionable. Infantry adopted aggressive screening tactics, advancing well ahead of tanks to suppress Panzerschreck teams before they could engage. Artillery and mortars delivered suppressive fires on suspected anti-tank positions. Despite these measures, the Panzerschreck remained a serious threat through the war's final days. German tactical innovation continually adapted to Allied countermeasures. Panzerschreck teams learned to target specific vehicle vulnerabilities, including vision blocks, track assemblies, and engine compartments, where additional armor was impractical. Multiple teams coordinated simultaneous attacks to overwhelm tank defenses. Urban combat tactics evolved to exploit the weapon's capabilities while minimizing exposure to return fire, firing from upper building floors, through windows, from rubble piles that provided both concealment and protection. These evolved tactics influenced post-war anti-tank doctrine worldwide. NATO and Warsaw Pact forces studied German Panzerschreck employment extensively, incorporating lessons learned into their own infantry anti-tank training. The concept of distributed anti-tank capability at squad level, pioneered by the American Bazooka and perfected by the German Panzerschreck, became standard doctrine for modern military forces. Production quality control data survives from several facilities, providing insight into German manufacturing standards under wartime pressure. Random testing of production weapons showed approximately 95% met specifications in 1943, declining to roughly 80% by late 1944. Primary failures involved ignition systems, magneto mechanisms that generated insufficient electrical current and tube integrity issues, where welding quality declined as skilled workers were conscripted for military service. The economic impact extended beyond direct production costs. Germany diverted significant industrial capacity to Panzerschreck manufacturing, including steel production, electrical component manufacture, and chemical facilities for propellants and explosives. The program consumed resources that might have produced other weapons systems. However, the cost-effectiveness compared to traditional anti-tank guns justified this resource allocation. From Wehrmacht perspectives increasingly focused on defensive operations where mobility mattered less than firepower density. Training programs evolved continuously based on combat experience feedback from frontline units. Initial training emphasized mechanical operation and basic marksmanship. Combat veterans later provided practical instruction on camouflage techniques, position selection, escape and evasion after firing, and small unit tactics for coordinated anti-tank operations. The Wehrmacht published numerous training pamphlets and tactical guides specifically for Panzerschreck operators, materials captured and translated by Allied intelligence that now provide historians with detailed insights into German anti-tank doctrine evolution. Supply chain complexity increased as production expanded across multiple facilities and occupied territories. The weapon required specialized components from numerous suppliers, electrical contacts from precision manufacturers, optical sights requiring glass grinding facilities, steel tubing from rolling mills, wooden stocks from furniture manufacturers, and propellant from chemical plants. Rocket production demanded separate facilities for warhead manufacture, propellant mixing, fusing assembly, and final quality control. Disruption at any point could halt production downstream, making the entire system vulnerable to Allied strategic bombing campaigns. The Panzerschreck program ultimately demonstrates rapid military adaptation under extreme wartime pressure. From initial capture of American bazookas in November 1942 to mass production beginning September 1943, Germany transformed a foreign concept into indigenous capability in just 10 months. The program succeeded through pragmatic engineering that adapted existing German resources, particularly 88mm warheads already in production, rather than developing entirely new technology from scratch. Germany's ability to produce nearly 315,000 Panzerschrecks while fighting a multi-front war against enemies with overwhelming industrial superiority reveals remarkable organizational resilience. The weapon emerged from systematic reverse engineering that identified and corrected original design weaknesses rather than slavish copying. German engineers didn't simply replicate the American bazooka, they created a substantially improved weapon system that exceeded the original in every measurable performance criterion from penetration to range to reliability. The historical significance extends beyond technical achievement into broader questions about technology transfer and military adaptation. The Panzerschreck represents successful battlefield technology acquisition under combat conditions, rapid industrial mobilization despite severe resource constraints, and effective military adaptation to enemy innovations that German doctrine had never anticipated. The program proved that captured enemy technology could be quickly transformed into mass-produced indigenous weapons that materially influenced battlefield outcomes. Modern military historians study the Panzerschreck as a case study in successful reverse engineering, rapid product development under wartime conditions, and industrial mobilization in resource-constrained environments. The timeline from battlefield capture to mass production remains impressive even by contemporary standards, with modern computer-aided design and flexible manufacturing systems. Few programs have achieved similar speed from concept to deployment, particularly when starting from captured enemy equipment, requiring complete engineering analysis and manufacturing infrastructure development. The complete story encompasses technical innovation, industrial achievement, and human tragedy that cannot be separated from the weapon's history. While German engineering deserves recognition for rapid development and successful mass production under difficult conditions, the extensive use of slave labor cannot be ignored or minimized. Tens of thousands died producing weapons that extended a criminal war already lost. The Panzerschreck's history includes both remarkable technical achievement and systematic exploitation of forced laborers whose suffering made that achievement possible. The weapon's legacy in modern military thinking remains significant. The distributed anti-tank concept, pioneered by the American bazooka and refined by the German Panzerschreck, became foundational doctrine for infantry forces worldwide. Every modern military equips infantry squads with portable anti-tank weapons descended conceptually from these World War II rocket launchers. The Soviet RPG series, American AT-4, British LAW, and Swedish Carl Gustaf all trace their operational concepts back to the revolutionary idea that individual soldiers could defeat armored vehicles without crew-served weapons or vehicles. The engineering lessons learned influenced post-war weapons development across multiple domains. The shaped charge principle pioneered in these shoulder-fired weapons became standard for anti-tank munitions, from tank guns to attack helicopters. The concept of accepting design simplicity to enable mass production influenced everything from assault rifles to surface-to-air missiles. Military procurement philosophy shifted gradually toward American-style emphasis on adequate solutions in large quantities rather than perfect solutions in limited numbers. A direct lesson from studying how German technical superiority was overwhelmed by Allied production capacity. In conclusion, the Panzerschreck stands as history's most successful reverse engineering program, transforming captured American bazookas into approximately 315,000 improved German weapons in under 1 year from capture to mass deployment. The program demonstrated that military innovation could be borrowed, improved, and mass-produced faster than previously believed possible, even under conditions of total warfare and increasing resource scarcity. From the first battlefield captures during Operation Torch in November 1942 to the final weapons produced in April 1945, the Panzerschreck represented German industrial capability and engineering pragmatism applied to desperate military necessity. It proved that even losing powers could achieve remarkable technological adaptation when survival demanded it. The weapon's influence on military aid, thinking about portable anti-tank warfare, reverse engineering methodology, and wartime industrial mobilization continues to resonate in contemporary defense planning and weapons development programs worldwide. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.